Well, here I am in the comfort of your own home, helping you with your math homework tonight. What a special privilege that is, isn't it? And I thought maybe I'd do a problem with you and get you started, because compound inequalities can be a little difficult to grasp at first, but once you understand what they're asking for, you'll latch onto it right away. Compound inequalities, that's what I'm trying to write over here on this side. Equalities, my pen's a little thin. Okay, here we go. So let's look at problem 7. Now, what is this problem saying? It's saying some number plus a negative 3 has to be less than or equal to negative 2 and greater than negative 4. Find any number that will make that true. Now, you notice I kind of pulled out the word and very elongated, because really what's going on is we have a conjunction statement, kind of like in English. You have a conjunction. And we could split it up into two separate individual inequalities. So we could say that we have negative 4, whoops, that was not supposed to be less than or equal, right? It's just supposed to be less than, okay? So what this says is we have all real numbers, D, adding to a negative 3 is greater than negative 4, and remember, and means where we have overlap. It makes both of them true. Negative 3 plus D. So all real numbers adding a negative 3 is less than or equal to 2. So what numbers would make both of these inequalities true? Well, let's go ahead and isolate D. So we're going to add 3 to both sides. So we end up with negative 1 is less than all real numbers of D. Or we could say all real numbers that are greater than negative 1. That would make that inequality true. Now, if we add 3 to this side, so now we get D is less than or equal to 5. So that says all real numbers less than or equal to 5. So what I'm going to do on my number line is I'm going to go from I want to make sure I include negative 1, and I want to make sure I include 5, because those are my boundary points. So I'm going to, now make sure you use a straight edge. It's a little hard for me to use a straight edge on this iPad. Okay, so here's my number line, and I'm going to graph each inequality and look for where there's overlap. So all real numbers greater than negative 1. So that means I don't include negative 1, but it's all real numbers greater than negative 1. And then the second statement says all real numbers less than or equal to 5. So I include the 5, but it's all the real numbers less than or equal. Now the solution to this inequality is where both of them are true. So I can see that here is a boundary and here is a boundary. Now how would I write that out? So it's all real numbers D that are less than or equal to 5, because the 5 is included in both inequalities. And then it's greater. Now, does it include the negative 1 for both inequalities? No, it does not. So it's just greater than negative 1. So any number that is greater than negative 1, but less than or equal to 5, will make both true. Now, I hope that helps you understand. Would you like to do another one with me? How about... Okay, so one of the OR problems, let's see if I can find one. Number 13. So number 13 is y minus 2 is less than negative 5, or, whoops, that or doesn't look very good. We have y minus 2 is greater than 5. Now remember, with or, we're looking for, it can be one or the other, okay, wherever I see numbers that make it true. So I'm going to solve for y, so that means I'll add 2 to both sides. So y is less than any number, y is all real numbers less than negative 3. Now on the other inequality, if I add 2, all real numbers that are greater than 7. So what I'm going to do is I'm going to graph this inequality. Now when I graph it, I want to make sure I include the boundary point of negative 3 and the boundary point of 7. So maybe I'll start at negative 5, negative 4, negative 3, and I want to make sure that I go up to at least 7, to negative 1, 0, 1, 2, 3, 4, 5, 6. Good, I made it to 7. I'll go a couple above it, okay? Great, and this is a number line that continues in both directions. So now, using two different colors, I want to graph all of the y values that are less than -3. So it's -3, I do not include the -3, but it's all of the values less than -3. Now for or, I want to see where one solution or the other is true. Now I'm going to graph the second inequality. Y is greater than 7. So I go to 7, do not include 7, but it's all the numbers greater than 7. So that means any number in any section that is shaded is the solution. So that means y can be less than -3, or it can be greater than 7. And any number in one of those regions would make this problem true. Okay? So now you complete the others and use these as an example.